In this video, we're going to be continuing based off our last video on half-life decay, except we're just going to be focusing on certain calculations, and the style of calculations you're going to see on your test or the provincial diploma. So my first example here says the half-life of a radioactive isotope is 2.5 years. If the activity of the original sample of the isotope is 3.2 times 10 to the 3 becquerels, what would be its activity after 5 years? Now, before we looked at it, we had masses. Well, if we think of it this way, becquerel is the amount of nuclei that decay per second. So if we think about it, if we have less mass, we're going to have less becquerel, or less nuclei decaying per second. So we're using, when we see becquerel, the same formula as what we did before. So let's start this off here. What do we know? I know my half-life time is 2.5 years. I also know my original becquerels, or my original decay rate, is 3.2 times 10 to the 3. And I also know the time frame of which this is going to be occurring over, and that's going to be 5 years. Now what I'm trying to find out is how much becquerels, or how much radioactive decay, is happening at the end of 5 years. Let's look at my formula. And now let's plug in everything we know. We have 3.2 times 10 to the 3 becquerels. We're multiplying by 1/2, and it's going to be 5 years out of my total half-life is 2.5. So altogether, if we simplify this, this is just going to be 2. So half squared is going to be a quarter. So if I want to take a quarter of 3.2 times 10 to the 3 becquerels, that's going to end up giving me 8.0 times 10 to the 2 becquerel for an answer. So that's going to be my decay rate after 5 years. In my second example, we have the half-life of a radioactive isotope is 6.8 years. If the activity of the original sample of this isotope is 4.9 times 10 to the 5 becquerel, what would be its activity after 100 years? So let's start off what we know. We know my half-life is equal to 6.8 years. We know my original amount of decay is equal to 4.9 times 10 to the 5 becquerels. We also know we want a total, it's going to be looking at a total of 100 years. And we want to find what decay rate will be in 100 years. So let's first look at my formula. And let's do my substitution. So we're starting with 4.9 times 10 to the 5 becquerels. We're multiplying that by 1/2. And that's going to be 100 over 6.8 years. When I plug all this into my calculator and I calculate out, I'm going to end up with 18.3 becquerels as an answer. So let's look at my third question. It asks what fraction of polonium-210 sample will remain after 172 days if the half-life of polonium-210 is 172 days. So some of you might already know the answer to this, but let's check it out by just looking at my equation here. So first, let's write down what we know. My time for half-life is 172 days. And my time that we're looking at for the half-life to occur is 172 days. Now, what do we want to know? We want to know the ratio of n, or the fraction of n over n naught. So that's my new amount of polonium over my original amount. So let's look at my formula. We're going to have, okay, now we're going to rearrange this. So we are going to have, and I'm going to have 172 over 172. So basically, my exponent is equal to 1, so my fraction of remaining substance will be 1/2. My fourth example, we're looking at a 2-gram sample of a radioactive isotope that undergoes radioactive decay. If the half-life of this isotope is 45 minutes, how much of this isotope will remain after 5 hours? My first thing I must convert here is I look at 1 times in minutes, 1's in hours. So I'm going to convert everything to hours. So I know my half-life time is, in fact, if we convert it to hours, 3/4 of an hour. Now we know my time elapsed is going to be 5 hours. And my original sample is going to be 2 grams. So let's look at my equation and then plug in what we have. Alright, so first of all, we know my original sample is 2 grams. We're going to multiply that by 1/2, and then we know my time is going to be 5 hours, so that's 5 divided by 0.75, which is 3/4. Now if I plug this into my calculator, I'm going to end up getting 1.9 times 10 to the negative 2 grams. So here we have a question from a provincial diploma exam. We have a graph here showing the decay rate of cesium-137. And the question asks, based on the graph above, what is the approximate half-life of cesium-137? Well, first of all, let's look what we're starting off here. Our maximum is 8, so my first half-life we're looking at is 4. And I go from 4 down, I'm going to have 30 years. And then even if we went from 4 to 2, if we look at this section here, we go from 30 to 60, it's again 30 years. So my half-life is 30 years. Doesn't matter which section we look at the graph, even if I went from 6 all the way down here to 3, I'm going to end up getting 30 years every time, no matter what. In our last question, we have a student that obtained samples of pure quantities of two radioactive isotopes, X and Y. The samples contain equal number of atoms. The half-life of each isotope is given below. The radioactive half-life of isotope X is 120 days. The radioactive half-life of isotope Y is 15.2 days. Both isotopes undergo beta decay. So now we want to know which of the following situations would result in a person experiencing the most exposure to radioactivity. So A says being exposed to isotope X at a distance of 2 meters for 2 hours. Well, isotope X has a very slow half-life. And if they both have an equal amount of atoms, that means we're going to be getting less radioactive decay per second, so less becquerels. So I'm going to assume it's not going to be isotope X. And the second one says isotope X again, except this time it is 1 meter away. So being closer, yes, we're probably going to get more radioactive activity. So now let's look at C. It's looking at isotope Y. Its half-life is lower, which means we're going to be experiencing more radioactivity. But we are 2 meters away. So I'm going to say C is no as well because we are too far away. So far these are all no. Now my last one is going to be isotope Y, which we know is going to be giving more radioactive decay, but it's only going to be 1 meter away for 2 hours. So we're going to be just as close, so my answer is going to have